When I tell people that I'm a software developer, I often hear as a reply, I never understood those numbers of yours. Today, I'd like to tell you somewhat about those numbers of mine, or more precisely, mostly lack thereof. Hello everyone, my name is Wojciech and you're watching Nonconformist. The job of software developer seems to be shrouded in a mystery to such an extent that a lot of people do not have a slightest idea about what we are actually doing during our workday. Plumbers assemble pipes and fix leaks, electricians lay cables, bricklayers are laying bricks, but a software developer, well, most likely works with some magical numbers that no one understands. There's even a joke about software developers that there are people who solve problems you didn't know existed in a ways you wouldn't understand. What I'd like to do in upcoming videos is to change that perception a little bit by telling you how a software developer develops the software. There are a lot of topics to cover, so this time we'll focus mainly on the origins of software development as well as on some basic knowledge about programming languages. Let's get started. It will be a lot easier to understand how do we develop software if we firstly establish why do we do that. And to answer this question we need to go back in time to early 1900s, which happens to mark beginnings of electronic engineering as we know it today. Electronic devices are made of various components: transistors, resistors, capacitors, diodes, sensors, displays, and others. Those components connected to each other form circuits that are able to perform more advanced tasks than the components themselves. The more complex electronic devices you want to design, the more components you will have to use, and as a result, the more connections you will have to make. This causes an obvious problem, because if you connect everything with wires, you will quickly end up with a web-like mess difficult to understand, maintain, let alone further develop. To tackle this problem, as early as in 1903, a famous German inventor, Albert Hanson, filed a patent for an invention which in time became what we know as PCBs, printed circuit boards. The idea of PCB is quite simple. Components are arranged on a flat panel made of an insulator, a material which does not conduct electricity. The legs of components are threaded through holes in the panel and then soldered to the layer of conductive material surrounding the holes. Finally, components are connected to each other by narrow paths of conductive material pre-printed on the panel. The invention of PCBs made life of engineers a lot easier. Having all connections pre-printed reduced the risk of making wrong connection between components or, worse, accidentally making a short in your circuit. Maintaining and repairing the circuit was also a lot easier. In addition, the amount of space needed for the circuit has been drastically reduced. There was another big advantage of PCBs. They were very easy to replicate. It was important not only because it allowed manufacturing complex devices in large quantities, but also because the design process of new devices was easier. And that's because engineers figured out that a lot of designs shared some common circuits in unchanged or mostly unchanged form. This observation led to next important invention, integrated circuits. Our journey in time brings us now to 1950s. The first integrated circuits were simply pre-assembled circuit boards coated with plastic or some other material. A set of wires was left on one side so that one could connect those wires to some other circuit, and you knew precisely how to connect them because each integrated circuit came with a manual and schematic which helped you integrate it in your project. A big breakthrough happened when engineers managed to create a monolithic integrated circuit, a component which nowadays is commonly called a chip. Imagine a whole circuit enclosed in a box of size roughly 1 by half by quarter of centimeter. This invention allowed designing PCBs which were an order or 2 orders of magnitude smaller than they would be without integrated circuits. And as an extension, this obviously enabled engineers to make even more complex designs. Among the many advantages, integrated circuits had one major drawback. If you wanted to change the way the circuit works, or even adjust some of the parameters that affects its behavior, you were out of luck. The only option was to use a different chip or replace it with a larger circuit of your own design. Everything changed in 1969 when a company called Busicom approached Intel in hope to collaborate into creating an integrated circuit for their programmable calculator. There was a catch though. Busicom wanted to use the same chip also in their ATMs and cash registers. It means that the same physical chip must have behaved differently based on which device it was installed in. Its behavior was stored in another chip called ROM, read-only memory, which contained a set of instructions interpreted and executed by the first chip. The collaboration ended up in a big success, which brought to the world first commercially available microprocessor called Intel 4004. This chip was one of first multi-purpose integrated circuits. You could redefine its behavior with a carefully designed piece of software. This brings us to a very obvious question. How does a program for such a microprocessor look like? To answer this question, we need to delve into topics of programming languages. Programs for microprocessors are written as a sequence of simple commands, and those commands are actually encoded as groups of numbers. Yes, we finally found those mysterious numbers of ours. Obviously, those numbers are by no means random. There is a very strict set of rules which define what specific values mean and how can they be combined together to achieve specific results. In computer science, such a set of rules is called a programming language. If you think about it a little, it makes sense. Natural languages also consists of set of rules describing how do we connect letters into words and then words into sentences to express various concepts. The same way as natural languages have names, also computer languages have names. For example, this numerical language designed for programming microprocessors is called a machine code. Let me show you an example of how a program written in this language looks like. You are now seeing machine code of a Windows program which displays Hello World inside a console window. If you are wondering if people actually wrote programs in pure machine code, the answer is yes, they did. And we are talking not only about the first microprocessors, but also more recent times. The page you now see shows a part of program listing published in a 30-year-old Polish newspaper called Tajemnice Atari, which translates into Secrets of Atari, that was dedicated to one of the first widely popular personal computers. The listing you saw is actually a whole program written solely in a machine code. All the lines contained commands expressed as numbers written in hexadecimal format. When you run it, all those numbers are loaded into memory and then executed by the processor. The bad news is that people did write programs directly in the machine code, but the good news is that extremely overwhelming majority of the current software development is being done without touching machine code even with a very long stick. So what can I say? Hello and goodbye magical numbers. The machine code is something software developers call a low-level programming. Let me elaborate on that for a while. It can be said that the ultimate goal of the evolution of programming languages is simply a natural language. It would be really cool if we could just express what we want to happen and then just wait for the computer to finish processing and produce results. The birth of technologies like ChatGPT may be a small step towards this goal, but in reality we still have a long way to go. The imaginary scale between the machine code, which is directly understandable by the processor, and the natural language, which in turn is understandable by humans, represent a way of dividing programming languages into categories. We call languages closer to machine code low level and those close to the natural language high level. Since we now know the extremes of this scale, let's take a look at a couple of languages which are somewhere in between. The next language in terms of its level, just after the machine code, but still very low, is the assembler. Let's take a look how the same program showing Hello World looks like written in this language. Well, it still looks kind of weird, but at least we start seeing some actual words which we can make some sense of, namely add, call, or read, which is a short form of return. You may be surprised, but the assembler is actually equal to machine code, except only for the fact that all the commands and their parameters are now written in a way which is a lot easier for a human to understand. So if you write a program in assembler and then want to convert it into the machine code, a special program which performs this task will only translate the commands into their numerical counterparts. We are still very low in terms of the level of programming language, so let's move a little higher and also closer to the present times. The 1970s were the moment when programming languages began to appear like mushrooms after rain. It was then that probably the most widely used language was born, the C. C is a language that no longer requires knowledge of machine code. The program Hello World, written in C, looks like this. Immediately, we begin to see some higher level concepts. The instructions are enclosed in curly braces, we see something called main and a command called print that gives us some suggestion about what the program actually does. It still may not be the easiest language to read, but even if you don't know much about software development, you should probably be able to guess what this program does. The really important thing is that C is no longer translated into machine code, but compiled instead. This means that a special program called a compiler reads the source code written by the programmer, analyzes it, and then generates machine code that is equivalent to what the programmer wrote. The machine code and assembler code that you saw earlier is actually the result of compiling code written in C that I just showed you. The next language in line is C++, which is the spiritual successor to C. You may be a little bit overwhelmed by the amount of strange characters, such as double colons or arrows, but the code is still much more understandable than the one written in assembler. As a final example, let me show you C#. This language in turn is the spiritual successor of C++ and is at a very high level. We no longer see strange character sequences like colons or arrows, but instead full names like program, console, or writeline. I can bet dollars against peanuts that if I showed you this source code, most of you would very quickly guess what this program does, provided you knew what a console was. C# still requires the developer to follow a strict syntax, but a lot of code written in this language resembles more or less sentences written in English. The programming languages themselves are a very broad topic, but I really don't want to go into details just yet, so let's stop at this moment. In today's episode, we learned why we started writing programs, what the program looks like at the lowest level, what those levels are, and how similar programming languages can be to the natural language. So now we know that the core of a programmer's job is generally writing code in some programming language. Finally, as you have seen, there aren't really many numbers out there, unless you really want to work with them. My name is Wojciech, and this was Nonconformist.